Bom dia a todos, boa tarde em alguns lugares. Obrigado por estar presente no nosso terceiro dia do evento. Good morning for all. Good afternoon in some place. Thank you for joining us today in the third day of this event. I would like to introduce our first speaker this morning, Professor Manuel del Pino, from Bose University, United Kingdom. He will talk about dynamics of concentrated vorticities in 2D and 3D Euler flows. Professor Del Pino has many remarkable papers in several subjects like harmonic maps, vorticity, blow-ups of solution, laws of compactness, etc. But for me, is more outstanding paper he wrote 30 years ago in collaboration with Patrice Felmer about local mountain pass theorem. Welcome, Professor Manuel del Pino. Please, the word is up to you.
Thank you very much, Olympia, for the very nice introduction. If I can ask, how many minutes do I have?
45.
45. Okay. So the talk today, I would like to speak about Euler flows, some topics concerning solutions with concentrated vorticities. Let me introduce the subject in the two-dimensional case. In the two-dimensional case, we consider the Euler equations for in vorticity form. This is why I call it V. For the Euler equation for an incompressible fluid, so it takes this form. It is a transport equation where the transport term is the gradient pair of psi, where psi is what is called the strength function, and is precisely the inverse Laplacian of omega. This is a non-local problem. I mean, you can think of it as a system or as a non-local transport equation, non-linear. And here, inverse Laplacian, say as it is customary, is simply a designation of the Newtonian potential in 2D. And I consider this system with an initial condition, say, in an interval 0t. Okay, so in what follows, this perp symbol means this, and the velocity field, by the way, if we want to recover the usual form of Euler equation, is recovered in this way. So this guy is precisely the velocity field using the Biot-Savart law. So the vorticity corresponds to simply the curl, okay, of the velocity, and it's given by this formula. Okay, concerning the initial value problem, this initial value problem is well understood in the two-dimensional case. In particular, there is famous theory, say maybe the most basic results are by Wolitner in 33 and then Judovich in 63, that in which it is proven that the initial value problem is well posed in L infinity. So if you start with something L infinity, solution exists at all times and remains L infinity. Not only that, if the initial condition is regular, not just L infinity, then the solution will be regular at all times. Let me make a simple observation, simple, however important. When written in the vorticity form, then we can see the following, that if if we consider a function that depends only in space, which is a solution of a semi-linear equation of this form. By the way, what I mean here is psi equals inverse Laplacian of the right-hand side when I write the equation in this way. Then it turns out that the pair psi omega, given where omega is precisely f of psi of x, yeah, is a steady state of V. Why is it so? Simply because the gradient, well, omega goes, if you compute the gradient goes along the gradient of psi at x, right? And you have here the gradient perp of psi, so the dot product is 0. And since there is no dependence on time, everything is 0, so we have a steady state. So all solutions of this form, of an equation of this type, local semi-linear PDE, are steady states. Let me fix one example that will be for me important, okay? If you consider the solution, the standard finite mass solution for the Euler equation, minus Laplacian psi equal e to power psi, I am in 2D, okay? Then it turns out that if you define omega, say that if e to power psi is this quantity, 8 over 1 plus x squared, this is called the Kaufmann-Cooley vortex. So psi is the log of this simply. And and if we compute the mass is precisely 8 pi. It turns out that for Lewis equation, entire solutions with finite mass are all known, and they are simply suitable scalings of this fixed function, and they all have mass 8 pi. So what I would like to do in this talk, or in the first part of this talk, is to describe the evolution of solutions to the Euler equation in vorticity form, where the vorticities are concentrated around a finite number of points. So I consider vorticities that look approximately, I mean, the vorticities I am interested in, or all functions I am interested in for the solutions, are smooth. However, very concentrated, so that omega, for instance, can be written as some superposition of Dirac deltas centered at moving points, psi j of t. Correspondingly, if I take inverse Laplacian of the Dirac delta, this is the fundamental solution, right? And so putting the 8 pi has to do with the Kaufmann-Cooley vortex. Huh? This is just a normalization, it's nothing special. But the psi, the inverse Laplacian of Dirac delta multiplied by this constant, becomes this function. Okay? So we may wonder, can we say that omega, psi, this pair, which are singular functions, constitute a solution of the equation? That issue is not so simple, not even in the two-dimensional case. However, formally we can compute conditions on the center psi j, so that formally these guys represent a solution. So I am interested in solutions then that are highly concentrated at a finite number of points, and the center of the points are moving. This is my situation. Well, these solutions, maybe because of people think of cyclones or tornadoes and so on, are natural objects in fluid dynamics, and they have their analysis has a very long history. The history of these concentrated vorticities traces back to important foundational work by Helmholtz in 1858, many years ago, later on by Kirchhoff, and then other people in the subsequent decades. To summarize what was obtained for these formal solutions that are highly singular, right? I mean, they are just distributions. Then, of course, we should have, as I mentioned before, that psi associated to this, the string function is the inverse Laplacian of this, and this is this function, where gamma of x is 4 log of 1 over x. So we compute formally. We introduce these objects in the operator defining the equation, and I get, if I differentiate omega, I get gradients of delta multiplied by the derivative in time of the centers, right? I get this quantity. And the second guy is a double summation, right? Because psi s and omega s are summations. And the elements in the summation have these coefficients included and these singular objects. Well, you might say, I have the gradient of the Dirac delta, which is a horribly singular object, right? Well, I don't know if horribly, but very singular. And on top of that, I have this gradient perp, which is also singular. Things could go terribly wrong, perhaps, if we consider I equal to j, because we have this very singular distribution multiplied by this singular function. That may have some problems with definiteness. In fact, it does. On the other hand, yet formally, we may consider the following situation. Delta, Dirac delta is a radially symmetric function. Gamma is also a radially symmetric function, right? So in the formal sense, it is natural that gradient of a radial function times gradient perp of the radial function is going to be 0, right? It's r hat times r hat perp. So for I equal to j, the very singular case disappears. And what we are left with, if I make the corresponding substitutions, I get the sum over j of these terms here plus this additional quantity. Sorry, here the a pi shouldn't appear. That's the typo. So what we get after this is that I will have a solution, at least in the singular sense, I will have a solution provided that these coefficients are all 0. Okay, and these coefficients being all 0, if you make the computation of these quantities and evaluate that x equals psi j, because remember, this distribution is only supported at psi j, so we need that the coefficient is 0 exactly at x equals psi j. So what we need is that this, when I plug in here psi j, I need that this is 0, and that amounts to this system of differential equations. Okay, so this is an n-body problem that involves the gradient. It's a Hamiltonian system involving the Newtonian potential. And so the centers move according to this Hamiltonian law. Okay, concerning this n-body problem, I can ask the following situation. This was found many years ago. What is less clear is how representative of the true Euler equations the system is. So the question to answer is, are there solutions, true solutions, smooth solutions of the Euler equation that behave as very concentrated functions around this finite number of points that move accordingly to this law? So this is the question. Are there true solutions, smooth, of system V with vorticity highly concentrated over a finite set of points which evolve by a dynamics approximated by this limiting configuration? The answer is yes. The answer is yes, and what I will show you is an answer fairly precise in that sense. What I consider then, I used the previous notation, omega s and psi s for the singular objects, these limiting singular objects. And I will use a regularization of the Dirac deltas using a Kaufmann-Cooley vortex. Yeah? The Kaufmann-Cooley vortex is this function which decays relatively fast, right? Has finite mass a pi. And when if I scale it this way, what I have is a highly concentrated function with mass a pi. So when epsilon goes to 0, this, in the distributional sense, approaches Dirac delta. So this is a regularization of this Dirac delta guy here. This is one possible way of regularizing. I choose this one because it is convenient for the purpose of my construction. And I have associated to that a corresponding regularization of the string function, which of the singular string function, that becomes this one. So it's simply this x minus ij to power 4 is replaced by this quantity. Okay, so simply add epsilon squared inside, and I get the corresponding regular objects. So the question that I will formulate about the regularization is there a solution of the equation which is close to these regular objects? And the answer is yes. And in fact, maybe, well, here is the observation that I made, that the omega 0 epsilon goes in the limit, the distributional way, to the corresponding combination of Dirac deltas, right? I am missing the 8 pi here. And the corresponding energy, so the velocity, this is the kinetic energy, this is the velocity field squared, the density. If when normalized by dividing by log epsilon, we get that it goes to a superposition of Dirac deltas with these weights. Our main result is that for a given collisionless solution, a solution without collisions of this system, there exists a solution of the Euler system in vorticity form that differs little from this psi 0 epsilon omega 0 epsilon. So it is very regular. All these scalings are based on the same limiting function, and there is a solution that looks exactly like this, where the centers evolve. The centers can be regarded as functions very close to this psi I. So this is a joint result with Juan Davila, Monica Buso, and Junchen Wei. Then the statement goes like this. If we have a collisionless solution of system K, of the Kirchhoff-Roth system, the ODE system, then there exists a solution, omega epsilon psi epsilon, of problem V, which is the Euler system, which has the form omega epsilon is equal to this nearly singular guy, plus some remainder phi, which is comparatively much smaller. And psi epsilon, similar to correspondingly to this regularization of the fundamental solution, plus the remainder psi. We are able to find the following estimates. In fact, the estimates can be substantially improved, but in principle, what we can say is that this remainder phi can be bounded by a small power of epsilon, a fixed power of epsilon, times the behavior of this bubble itself. So this phi is truly small order. And the psi epsilon, well, here is even more dramatic. This function, this little psi, is even size epsilon squared. So it's really small. Okay, so this is our main result. Then with this convention, we have, in particular, the validity of this with the 8 pi's here that I forgot, sorry. Maybe I should mention that before our results, our result, there was a previous result with this flavor by Marchioro and Pulvirenti, in which they act using mainly the distributional form, and the result they find is very nice. However, they are not in principle able to capture the asymptotic shape of these functions near the vortices. So that was our main point, was to clarify that by a constructive method. Okay, how does the proof goes, or the construction goes? The improvement, the construction has several steps. One of them is to construct a very good approximation, which is of high accuracy in powers of epsilon. Yeah, and this improvement of approximation is using by solving in an alternating way equations that are elliptic and transport. After doing that, we set up the problem in the form of a coupled system of inner problems near the singularities expressed in the scaling natural for the singularities, and an outer problem which is more regular, and that system is what we solved, what we actually solved, and we call it the inner-outer gluing scheme, the formulating that system. And finally, what we do is to find a priori estimates for the system, and to eventually solve it by a continuation argument using the Rayschauder degree. Okay, to give you a further flavor of how the proof goes, let me show you how does the step of improvement of the approximation go. So I will denote in what follows gamma 0 of y, this log, which is the solution of the Liouville equation, I remind you. And then what I am looking for is for a string function that has this form. This is the regularization that I was looking for. So this is just a rewriting of this. It's just that, of the rewriting of this function here. Okay, so I can write in terms of gamma 0, and I get this. And then what we want to solve is the system E omega psi equals 0, where E is the Euler operator, and psi and omega are related by this equation. And then I do the following. I change variables x into variable y, where y is this scale thing. So I center the variable x at psi j, and later, in addition, I scale it with this epsilon size. So what I will look for is a solution psi of the form psi 0 epsilon, this guy, plus this remainder, which it is convenient for me to write it in this form. So it is convenient to express this remainder in terms of the variable y rather than directly in x. Correspondingly, omega will be simply the Laplacian of this. The Laplacian of this function is simply this, 1 over epsilon squared times u0 of y, plus u0 of y is this bell shape that which is the argument of this log, and plus a remainder that it is convenient for me to write it in this form. Okay, so the new system, the equation or the Euler operator can be written in this form in terms of this remainder phi and the remainder little psi. The Euler operator becomes this. So I want to make this approximately equal to 0. This is what I would like to do. Okay, then what we have now is that psi 0 epsilon can be written in the following way. It can be written as kappa j gamma 0 of y plus this function that I am calling simply phi of x plus smaller order terms, where this phi of x is nothing but this linear combination of the function's fundamental solutions, right? But centered at the points far away from the given point j. I am doing this only around the point psi j. Then by assumption, I have the Kirchhoff-Roth system satisfied, so psi j dot is equal to this. This is just a first approximation. And hence we get the validity of this relation down here, where this r is of order epsilon squared y squared. So in summary, what do I get? I get that when I plug in this thing here, what I get is that the operator becomes epsilon squared phi t plus this term here, where this r is of order epsilon squared y squared. Now, if I write f of u to be e to power u, and since u0 is f of gamma 0, then I find that I can write the Euler operator in the following form. Look at this. This is a linear equation in phi. Psi is just the inverse Laplacian of, Laplacian psi is phi. So this is a linear operator in phi plus these remainders. You have these remainders. This is also linear. These are linear operators, and this is quadratic. But but you have things like this that are homogeneous. I mean, they don't depend on phi of psi, and this is nothing but the error, the first error. The zero-order term corresponds to having simply evaluated the error term in the when phi is 0 and psi is 0. If you do that, you just get this guy here, gradient per of r, gradient of 0. This function, gradient of 0 decays like power 5 of y, and the gradient of r is linearly growing in y. So this total thing arrives to epsilon squared times y to power 4. We will obtain a reduction in the size of the involved error by solving the following elliptic equation. Look at the operator. If I am able to find a psi such that this plus this cancels, then I will get an improvement of the approximation. If I solve this elliptic problem, then I will have solved, I will have been able to find an improvement of the approximation. And we can solve it. And we can solve it thanks to the fact that these are, this function gradient per of r is in reality at mode 2. If you expand in Fourier series around the origin, these quantities, then we are able to solve this equation. The bad guys are radial functions in the right-hand side, because radial functions actually make the linear operator vanish. They live in the kernel. All radial functions live in the kernel. This is a very degenerate operator. Okay, after improving sufficiently the approximation, we solve the problem by a continuation of degree argument, which near xij reads approximately like something like this for an error. After we do sufficient approximations, we arrive at epsilon to power 5 times rho to power 3. The basic ingredient that we use to prove the a priori estimates, a priori estimates is essentially what we need is to solve this using some linear theory. What we are able to prove, and this is a very important step, is that phi has center of mass 0 in a large ball and mass 0. Then the solution to this initial value problem with initial condition 0, okay, can be bounded in the following way. This is a way we have these L2 weighted estimates, L2 in space. So this is what we have. We lose epsilon squared just as if we were solving the ODE here. And this is why you have this epsilon to minus 2. And in addition, you lose this log epsilon quantity. So, and this allows, finally, a fixed point scheme to work if you start with E with the power 5. The reason why you need power 5 is because you have quadratic terms. So, since if you start with 5, then you improve the error to 6. So this is the reason why we use power 5. With power 4 alone is not enough. Okay, let me mention some non-trivial extension that we have been able to find recently in joint work with Antonio Fernandez, my former postdoc. Now he's in ICMAT in Madrid. So our result is the same, except that now it is for the Quasi-Geostrophic Equation, which is another celebrated object broadly studied, in which the inverse Laplacian is replaced by the inverse of fractional Laplacian. So the Newtonian potential associated to fractional Laplacian S is this potential here. Yeah, we are able to find a similar result, of course, with this dynamics replaced by something else. In fact, the new dynamics looks like this, and now the core functions, the core function U0 is this function here. These correspond to the bubble of the critical exponents, like the Van Talenti bubbles for the critical equation, the critical fractional equation. This is what we use here to implement the theory. We cannot do it, unfortunately, for every s up to 1/2, even though we believe it is true, because it becomes complicated and it becomes quite technical, and a number of obstructions appear in the way. We are able to arrive to 9/10, okay? But it is a quantitative amount of how much you can go below the Euler case. So the proof is much harder because, in particular, you need to make arbitrary order approximations, which is not so trivial, and a priori estimates that are a little bit, quite a bit more complicated. Anyway, a special case of this is the traveling wave solution for the case of a traveling vortex pair. And this is a result we found with Ao, Davila, Musso, and Wei, that is recently published. And it is, of course, just a very special case, no? That reduces to an elliptic equation. That's important to say. Partial results of this type had already been found by other authors that I mentioned here. And as I mentioned, we use a similar scheme as in Euler, but more difficult. Let me mention an important point. The initial value problem for the equation, the initial value problem is not well posed. It's not known. And that is a difficulty that we have to avoid. And the theory of Udovich does not apply. So really, we have to use the full power of the construction. We construct the solution directly, rather than relying on some theory. Okay, and here what I mentioned before, the lack of regularity of the transport term is a central issue, and it becomes more irregular as you go down in S. So we need a high accuracy of the approximation, and eventually with arbitrary large order, we can arrive in reality up to this number. Okay, let me now show you like a little discussion about the three-dimensional case. The three-dimensional case is a very exciting subject. It's the motion of vortex filaments, not just vortices, not just points, but rather, this is more realistic, right? Say the evolution of curves or regions that the near curves that move in time and where vorticity is highly concentrated. This is the case of vortex strings. This is a true image. I suppose this is just artistic, okay? But it's a true image from a volcano in Italy. Okay, so the open question that I would like to mention to you now is called the vortex filament conjecture, that comes from the work, the very origin of Helmholtz. It was explicitly formulated with a formal computation by Darrios and later Levi-Civita. Say Darrios was a student of Levi-Civita in 1906. So let me tell you what that vortex filament conjecture is. We consider the Euler equation now in 3D. In 3D, the form of the vorticity is a little bit more complicated. Omega now is a vector. This vorticity is a vector. It's a vector which is the curl of the velocity. And the velocity can be computed by the Biot-Savart law, which is this, where psi is this guy here. Okay. So what we want to find is solutions with vorticity concentrated on a time evolving curve, yeah, parameterized by arc length, say. And what we would like to find are solutions with vorticity concentrated in a small neighborhood in a tube of radius epsilon, let's say, around this curve gamma of t, and where the vorticity itself, which is a vector, in the limit goes along the tangent vector to the curve and multiplied by a Dirac mass. So omega epsilon approaches as epsilon goes to 0, this distributional form. Yeah, this is the extension of what we were doing in 2D. So, but now this is a vector quantity. The law discovered by Darrius was the following. If I change time into this form, rescale it with the log epsilon factor, then, and I then consider a curve evolving by this law, which has a very specific name. This is the binormal flow of curves, the flow by the binormal vector. It is maybe less known than the curve shortening flow, in which this binormal vector is replaced by the normal vector, but it has very different it has very different characteristics. For instance, this flow preserves length, and it is not a parabolic equation, but a dispersive equation, like Schrödinger type. So this is the binormal flow of curves. So B denotes the binormal vector and T the tangent. Here is the normal. Okay. So the vortex filament conjecture is that we can actually find a solution with that behavior. So given a solution of the evolution of curves by the binormal flow, I can find a true solution smooth omega epsilon to the Euler equation, so that after I do this scaling, I get this approximation to Dirac delta along the curve multiplied by the tangent vector. Okay, what is it natural? Say it is to consider, just because of what we did in the previous thing, I consider again the Kaufman-Scully vortex, and I simply replace delta, I regularize it by this scalar function. So what I look for is a solution of approximately this form. This is our answers. Let me tell you that we have been able to establish, at least in a very special case, this conjecture. And it was already known, not directly with this profile, but similar, by in another situation. Let me tell you right away what I mean. The situations where the conjecture is known are a vortex ring traveling vertically, okay? Traveling vertically with constant speed. That's a solution of the binormal flow. No, if you take the suitable relation between radius and the velocity of propagation. The same for a helix with the right parameters, a helix that is rotating with constant speed around its axis. That's also another example of binormal flow. And in both cases, it is known that the conjecture exists. Namely, there exist solutions that go along this motion. And these ones here are very well known, and they are called vortex rings. This one is less known, and it is something we found recently. In fact, in the case of 3D Euler with helicoidal symmetry, say we can reduce the problem to an elliptic equation. Okay, we make change of variables involving time and so on, and we eventually find to solve what we need to solve is an elliptic equation that has this form. It's one of the usual semilinear equations, and we use singular perturbation methods to solve it. This is what we do, and that's our result. That if we choose again the vortex cooling, the Kaufman-Scully vortex, what we need to solve is an equation of this form with the parameter epsilon here, and that eventually goes to Dirac delta, and the curve gamma, which is the limiting curve, goes like this. These solutions don't change form in time. They are traveling waves, if you wish. This is why the problem reduces to an elliptic. And the helix expressed like this is a solution to the binormal flow. Okay. The other situation known for the binormal flow, as I mentioned, was the vortex ring. This come from foundational work by Frankel in the early 1970s. He was able to find, with the corresponding ansatz of axisymmetric solutions with no swirl, he reduces the problem to an elliptic equation, or to a variational problem, I should say, and then a solution is found using different arguments. And people later on, especially notably Ambrosetti and Struve, also had work in the same direction using variational methods. Let me tell you one situation that does not reduce to an elliptic equation that is very interesting. It is a law discovered by Helmholtz in 1858. I mean, it's kind of surprising, but what he got the intuition was that if you have these two rings interacting, two vortex rings interacting, one single vortex ring is something that doesn't change shape and goes with constant speed to the right, let's say, okay? But what happens if you put two vortex rings and you let them interact? Then you have a situation that is no longer something that doesn't change shape in time. And I tell you what happens. The red guy may be going faster and approaches the blue guy with a smaller radius. When it goes faster, the radius is smaller, and then it crosses. And then the blue guy starts doing the same, then reduces and crosses the red, and so on. Okay, here is another show of the situation. So what is the problem that we would like to attack? Is the mathematical justification of leapfrogging dynamics in the 3D axisymmetric Euler flow without swirl. In that case, the problem using the symmetries of this radial symmetry, this axisymmetric situation with Z, and then the problem is reduced to a two-variable solution, to a two-variable problem, where for a section of this scenario, and it is this equation, which is an Euler equation with weights, I should say, and what we are eventually able to find are solutions that go along with a specific flow for the radii of the rings. More specifically, if we have collisionless solutions of this ODE system, and we consider these centers, then we can find a true solution of the axisymmetric equation with these asymptotics, and that's it, and with the Kaufman-Scully vortex. Thank you very much for your attention.
Thank you, Manuel Pino, for the wonderful lecture in the interesting subject. Let's see if it has some comments or remarks. I have one just for curiosity. Why you cannot go below in the fractional case? I think work with Antonio Fernandez.
Yes.
Why you cannot go below 9/10?
Oh, that's a great question. Thank you. So the bottom line is that we are using this iteration procedure. And in this iteration procedure, you alternate the use of elliptic equation and transport. In this transport, it's not for free, the use of transport. Every time you use it, you lose powers of epsilon. And it turns out that somehow our scheme breaks down. If S goes below that threshold, we are not able to close the circle. It is perhaps the problem with our technique, but we don't know if it is essential. We suspect it is not essential, but we have not found a way to go around that.
Okay. Thank you. Let's see. Here. Just a moment. Okay. Okay. I think I does not have comment. Manuel, thank you very much for
Thank
your,
you. Thank you so much for the invitation.
yeah. Nice to see you.
Nice to see you again.
Bye. Thank you.
Thank
Bye.
you.
I invite all the audience to continue. We resume in 8 minutes.
Hi everyone. Welcome to the second talk in this morning. It is for me a pleasure to introduce Professor Andrei Zulkin from Stockholm University, Sweden. Today he's going to talk about normalized solutions to a non-variational Schrödinger system. Professor Andrei Zulkin has many contributions on variational and topological methods, not only from the abstract point of view, but also regarding its applications to PDEs in smooth or non-smooth frameworks. He is an inventive researcher developing, sometimes with the help of his collaborators, tools which are useful for many researchers on elliptic PDEs. Welcome, Professor Andrei Zulkin. Thank you for accepting our invitation. It is a great pleasure to have you in the workshop.
Well, thank you very much for the nice introduction, and thank you very much for inviting me. It's my pleasure to be here, and if my count is correct, this is my fifth virtual trip to Brazil.
Oh,
so,
nice.
What I will speak about today, well, let me just say, do you see full screen now?
Yeah. Not full screen, Professor?
Not full screen.
No, but we can see your screen. I think it's okay. Yeah.
Because I see full screen on my computer.
Okay. Please, go ahead.
Okay, so what I'm going to speak about today is joint work with Monica Klapp, and it is about elliptic systems. First, let me look at this system, which has been studied it has been recently studied by many researchers. And note that here we have kappa I, and we have kappa I is free for the moment, and ui, the L2 norm of ui is fixed to some Ri. So Ri prescribed, kappa I free, and these kappa I's will appear as Lagrange multipliers. Well, typical applications of such systems are mixtures of Bose-Einstein condensates and propagation of wave packets. And then the L2, for the condensates, the L2 norm is the number of atoms, and in nonlinear optics, it's the power supply. And also here, mu I, they will always be positive, and what they stand for is the interaction of particles of the same kind, and positive means that the interaction is attractive, and lambda will be either less than 0 or bigger than 0, and this means less than 0 means repulsive interaction between different particles of different kinds.
Sorry for interrupting you, Professor Zulkin. Sorry for interrupting. We can't see, in fact, your slides. Can we try to share the screen again, please?
Okay, let me just.
Oh, now I think we can see. Try to advance, please.
So I shouldn't have full screen. Okay. So now you see it correctly.
Yeah. Try to evolve, please. Try to evolve.
Okay. Let's.
The next slide. Yeah. Now you can see. Thank you so much.
Okay, so let me just repeat that mu I bigger than 0 means that the interaction between particles of the same kind is attractive, and lambda means the interaction between particles of different kind, and it will be either repulsive or attractive. So this is a system of two equations, and it's a variational system. And also there are numerous extensions. Many people have worked on this. one can have nonlinearities which are not cubic. One can have L equations instead of 2 equations. But all these results, at least the results we know of, are for variational systems. And now here is a partial list of people who have worked on these problems. It could easily be made much longer. So what I want to do here is to consider a system which is not variational, at least not in general. So in case of 2 equations, it looks like that. So we have, well, in order to have it variational, there should be some interplay between lambda ij and lambda ji, and also alpha ij and beta ij would need to be related in a special way. And for L equations, it looks like that. So now there is a summation, meaning that the ice particle interacts with all other particles. And also I will be interested in positive solutions, and I assume that ui are in H1 radial. So all functions, I assume that all functions are radially symmetric. And also these results, they are, at least the results we have are for in dimensions 2, 3, or 4. And here is the general bound for P. It should be bigger than 1 plus 4 over n. This is usually called a mass supercritical nonlinearity. And also P is less than the usual, the usual constant for the Sobolev embedding. And as I already said, mu I are positive and lambda ij either positive for all ij or negative for all ij. So these, if one looks at the time-dependent Schrödinger equations, they look like that. So we have here I d phi I dt, the t derivative. And we make the standing wave ansatz phi I equal to e minus chi I t ui. And it sees, well, it's immediate to see that the L2 norm is conserved under time evolution. And also note here that when we prescribed our I, kappa I cannot be chosen arbitrarily. So this means that the frequency cannot be prescribed. So next, what I want to do is to look at the uncoupled system. So we have, for each I, we have this equation, and we look for positive solutions in H1 radial, and again, the L2 norm is fixed. Well, this is, well, this equation is quite known, and one knows a lot about this, but we will need some additional properties which I will discuss later. Well, first of all, it's more convenient to consider this system. So we take the positive part of U, or well, not system, but an equation. For the moment, we have an equation, I is fixed. So we take the positive part of U here. Well, first of all, it's easy to see by the Pohorzaev identity that kappa I must, for solutions, kappa I must be bigger than 0. And also, if one tests the equations with U minus, one sees that U minus must be equal to 0, that is, U is non-negative. And by the maximum principle, it's in fact positive. Also, it is in fact known that all solutions are a priori radially symmetric up to translation. But all solutions will in fact mean the only solution in this case. Well, so if kappa I is 1, then there exists a unique positive solution. I will call it omega 0. And this is a result by Kwong and by Chen and Lin. And also it is known by a result by Ni and Takagi that this solution is in fact non-degenerate, which means here that the linearization has a trivial kernel. So now I move from omega 0 to omega I by this change of variables. And then one can easily see that omega I in fact solves the equation star. Let me repeat this equation. So kappa I will be equal to, so having chosen gamma I, we also choose kappa I. And also one can see by direct computation that the L2 norm of omega I and of omega 0 are related by this identity. And now if P is not equal to 1 plus 4 over n, then this exponent will be non-zero. So we can prescribe the L2 norm arbitrarily by choosing a suitable gamma I. And again, since when kappa is 1, there is a unique solution. So also here, omega I will be the unique solution, and it will be non-degenerate. And in particular, what we will do in what follows is to choose gamma I to get the L2 norm prescribed by Ri. And now if P is equal to 1 plus 4 over n, then this exponent is 0. So we will have that omega I and omega 0 will always have the same L2 norm. So there will be no solutions unless Ri is equal to this. And if Ri is in fact equal to the L2 norm of omega 0, then there will be a one parameter family of solutions given by this expression. But from now on, I will be interested in P which is not equal to 1 plus 4n. And maybe I should also say once more that P bigger than 1 plus 4n is called mass supercritical, less mass subcritical, and P equal mass critical. So now I take, I denote by SI the L2 sphere of radius Ri in this space. And now I have two functionals, the functional I with subscript I, which is defined on the whole space, and Ji, which is defined only on the sphere. And here are the expression for I, and Ji. So here, this term is missing. Now, of course, critical points of II are solutions to our equation, so to this equation. And one can also show that if the solution U is in SI, then it will be a critical point, or if U is in SI, it will be a critical point of I sub I, if and only if it is a critical point of Ji, and kappa I is given by this expression. And you obtain this expression by multiplying the equation by u in and integrating. So next thing to see is that omega I is the only critical point of I subscript I, therefore it is also the only critical point of Ji if kappa I is given by the expression on the bottom of this slide. Also, it is easy to see and is of course well known that omega I is a mounting pass point of I subscript I. And as it is non-degenerate, so it's a mounting pass point, it's non-degenerate, and moreover is isolated, so its Morse index must be equal to 1. And now if I denote the jth eigenvalue of the linear mapping corresponding to the Hessian of I subscript I at this point omega I, and I also denote by lambda j twiddle the jth eigenvalue of the linear mapping, but now I take the covariant Hessian of ji at omega I. And now by a minimax principle, it's easy to show that lambda j is less than or equal to lambda j twiddle. Now we have, well, for I, we have one negative direction, and then on the orthogonal complement, all directions are positive. So lambda 1 is less than 0, lambda 2 is bigger than 0. And now, assuming for the moment that P is mass subcritical, one can easily show that Ji attains its infimum at omega I. And this is shown in the following way. First, we have the Gagliardo-Nirenberg inequality, with delta as here. And then if one uses this on the expression for Ji, we got this inequality. And the exponent, this exponent is less than or equal to 1. In fact, it's less than 1. And it's less than 1 if and only if P is mass subcritical. So Ji is bounded below and it is coercive. Next, we have that H1 radial Rn is compactly embedded in LQ for Q between 2 and, the Sobolev exponent. This is a result by Walter Strauss. And using this, one easily sees that the infimum must be attained, and since there is only one solution, it must be attained at omega I. So now what we have is that lambda 1 twiddle, since the infimum is attained, lambda 1 twiddle is either 0 or positive, and now we also have this. So the Morse index of Ji at omega I is 0, and the large Morse index is either 0 or 1. But this is not so surprising because, we have an infimum, and moreover, we have, we have a PDE, but for radial solutions, it's an ODE, so the null space cannot have dimension larger than 1. So from now on, I assume that P is mass supercritical, and here it will be a little bit more interesting. Well, first of all, one can show that the Hessian of Ji has at least one negative direction. This can be shown, in fact, by an explicit computation. So we must have the first eigenvalue less than 0. On the other hand, we know that lambda 2 is positive, so lambda 2 twiddle is also positive. And the conclusion is that omega I is a non-degenerate critical point, and it has Morse index 1. And next, let sigma I be the stereographic projection from the, well, minus omega I is the North Pole. So we have sigma I inverse is a chart for SI. And now we take, well, in local coordinate, Ji will look like that. Phi I is equal to this composed with the inverse of the stereographic projection. And now sigma I takes omega I to 0. So we have that 0 is a non-degenerate critical point. And moreover, it's, well, now we are on the tangent space to SI at omega I, and we can decompose it into the negative part and the positive part. So the negative part is, we know that there is only one negative direction, so the negative part has dimension equal to 1. And next we take an ascending sequence of linear subspaces for the moment for this tangent space. And I start here with k equal to 2, y we will see in a moment. So f2i is the negative part, and then fki, I obtain from, by adding, going from k minus 1 to k, I add one dimension from the positive part of the operator. So what I have is that the dimension of fki is k minus 1, and moreover I can do it in such a way that the union of fki will be dense in the tangent space. And now finally I take E1i as the orthogonal complement of this tangent space in H1 radial. So it's not L2 orthogonal, but it's H1 orthogonal. And now I take EKI, I have FKI, and I add this single direction. Then EKI has dimension K, and the union of EKI is dense in the full space. Also, we need to assume that F3I twiddle is chosen in such a way, it can be chosen and is chosen in such a way that omega I is here. And now another important observation is that sigma I, well, it maps, if we take SI and remove minus omega I, and then intersect with EKI, then this will be mapped into FKI. And next, let me take the set which I call WI. It's we take VI corresponding to kappa I bigger than 0, where kappa I is given by this usual expression. And now we have the following lemma, that if one takes an open bounded neighborhood V of sigma I wi, an open bounded neighborhood of 0, then there exists kV such that for all k large enough, 0 is the only critical point of phi I in V intersect fki. So what this means is that if one takes a bounded neighborhood of 0, then for large k, there will be no false critical points for this finite dimensional approximation. And now an immediate corollary for that is that if one takes a bounded neighborhood V of 0 here, then we can find kV such that the Brouwer degree, now we take the gradient of phi I restricted to this finite dimensional subspace, and we take V0 intersected with fki. This degree is equal to -1 for all k large enough and for all V0 in V. And this is, in fact, this is easy to see. First of all, the degree, we have only, here we have only 1, 0 for this gradient. So by the excision property, it doesn't matter which neighborhood of 0 one takes. And finally, the Hessian has exactly one negative eigenvalue. So the local degree will be -1 by a known formula. And next, if we take L equations, then I call J, U1, UL the function of which we obtain by adding the JI's, and phi will correspond to this sum. And now the Hessian of each phi I has one negative direction. So the Hessian of the whole phi has L negative eigenvalues or negative directions. So the degree of the gradient of phi reduced to fk will be equal to -1 to the power L for large k. Well, what is important here is that the degree is non-zero. So now let me return to the problem we started with. Well, the idea is that to homotopy the uncoupled system, so with this removed, to the full system. And again, let me remind you about the assumptions. And now the first theorem says that if, in addition to these assumptions, we assume that lambda ij are positive. So the first theorem is about positive lambda ij. And now if we take alpha ij bigger than 1 plus 4 by n, and moreover this sum is less than p, then there exists, at least one solution. Now, if n is 2 or 3, and moreover, if p is less than or equal to this number, then, in fact, we can have this inequality. And here, let me point out that this is quite a strong assumption, but if one takes alpha ij equal to 1, then there are, one can choose parameters in such a way that, there are no solutions. And this is a result by Bartsch, Zhou, and Zhang, if I remember correctly. So this is probably this is too strong, but one cannot just take alpha ij equal to 1. And another thing which one would like to avoid, one would like to have alpha ij plus beta ij equal to p. And this, in fact, can be done, but under more restrictive assumptions. So next theorem, well, this time we take lambda ij negative, and dimensions are 2 or 3. And now I have no restriction on alpha ij separately, but the sum should be bigger than this and less than p. Here I cannot have the sum equal to p. And also here one would like to have 4 over n, but this we cannot get. And now I will call, by a solution, I will mean a pair kappa bar u bar which satisfies this equation, the system of equations. So kappa bar will be this and u bar will be this. So bars will be used for vectors. And now we need to consider this system. And note that if t is equal to 0, this is an uncoupled system. And if t is equal to 1, then this is a system we want to solve. And I will also abbreviate the right-hand side to this. Now, if we multiply the i's equation by ui and integrate, then we get kappa. Well, I call now kappa I by kappa I t, or kappa I t of u, and it's equals to this expression. And also, we will look for solutions which are contained in this set ut, where note that an additional restriction that I put here is that kappa itu is bigger than 0. Well, first, what one can show is that if u bar is a solution, then kappa it cannot be 0 for any t. And if lambda ij is bigger than 0, then one needs the dimension restriction n less than or equal to 4. And this is a result by e comma. It's if minus Laplacian ui is bigger than or equal to 0 and ui is in this Lebesgue space for some q less than or equal to n by n minus 2, then ui is equal to 0. And it's easy to see that, well, we know that ui is in L2 and L2 up to L2 star. But if in 4 dimensions we will get, in 5 dimensions or more, we will get that q is less than 2. And then we don't know if ui is LQ. So this is the reason for restricting the dimension. And for negative lambda ij, one needs n to be less than 4 and also this. Well, the proof is by a certain comparison argument and these restrictions n less than 4 and this inequality, they just pop up. And also, if u bar is in ut, then one can show that all ui are positive, and this means that if kappa u is a solution to pt for t equal to 1, with u in u1, then it's a solution of our problem. And also another thing that is important is that FIT is a completely continuous operator because this embedding is compact, as I mentioned earlier. So now a few words about the proof. Well, now a solution, U bar, I will mean a solution which is in UT. And these U are well localized because there are no solutions on the boundary. Well, first of all, there are a priori bounds which are always necessary to use the degree argument. First of all, one can show that all solutions to PT are uniformly bounded in L infinity. And the proof, in fact, it uses a well-known argument. It's due to Gidas and Sprague for one equation and to de Figueiredo and Young for a system of two equations. Next, if this sharp inequality is satisfied, then the argument goes through under the assumptions of each of the theorems. And if alpha ij plus beta ij is p, for either for some or for all ij, then for the argument it is necessary to have lambda ij positive n less than 4 and p less than or equal to this exponent, this number. And now if lambda ij is less than 0 and alpha ij plus beta ij equal to p, in fact there is a result of Dancer, Way, and Veit, which suggests that there may be no a priori bounds. Well, it suggests because their result is in bounded domains, they can show that for a certain system of two equations, in fact, there exists a sequence of solutions which are unbounded in L infinity. And now we have UI is L2 bounded, L infinity bounded, so it's bounded uniformly in LQ for all Q, including from Q between 2 and infinity. And also using this in the equation, one sees that it's also bounded in H1 radial. And kappa I must be uniformly bounded. It's easy to see that it is so. And moreover, we have that kappa I are bounded, uniformly bounded away from 0, and the L2 norm of the gradient is also L2 bounded away from 0. Now, if one wants to show that A2 exists, one multiplies the equation by UI, integrates, and then one uses the Galliardo-Nirenberg inequality. And for alpha ij bigger than 0, it is in fact necessary to have this restriction. And if lambda ij is less than 0, then alpha ij bigger than or equal to 0 suffices. And this having the gradient, L2 norm of the gradient uniformly bounded away from 0 is very important for the argument. And also one shows that the set of all solutions is compact. And now let me recall that SI is the L2 ball of radius Ri, and also the tangent space to SI is, they are simply functions V which are L2 orthogonal to UI. And now let me take H1 radial and iterate it L times. So this is script H, and T is the torus S1 times S2 and so on to SL. And now I introduce an operator which goes from H to H1 radial, and it's given by this expression. And now note that if SITU is 0, or if SITU V is 0 for all V, this means that SITU is 0, and integrating by parts, one sees that then U will be a solution of our problem. And here we have kappa IT again equal to the usual expression. And now if U bar is in the torus, then by the very choice of kappa I, we have that this is inner product is equal to 0. So this means that SIT twiddle at U is H1 orthogonal to UI, but not L2 orthogonal. So this is in general not in the tangent space. So we bring it to the tangent space by taking this projection, orthogonal projection, and SIT without twiddle is equal to QUI and SIT twiddle. So we have here that ST goes from the torus. ST goes from the torus to the tangent space to the torus at U bar. And also one sees that U bar is a solution of our problem if and only if this is 0, if and only if this is 0. So what I want to show now is that there exists U bar which satisfies this equation. Now I take sigma of V. It's it consists of stereographic projections which go from into the Cartesian product of tangent spaces of SI. So we have the Cartesian product. We have the tangent space at omega to T. And now let me recall that the FKI were subspaces of the tangent space, and EKI were subspaces of H1 radial. And I also define FK by taking the Cartesian product, and EK likewise. And now PK is the orthogonal projection. So now I define a mapping GKT. Note that here we take V from the tangent space and restriction to FK. So sigma inverse takes V to UT intersect EK. And now we apply ST here and take the projection PK. So in this way, we are on the tangent space to the torus. And now we also take sigma prime. This is essentially, it's a mapping between tangent space to the torus and the tangent space to this. So now, when is this equal to 0? Well, it's easy to see. Well, this is an isomorphism, so this must be 0, meaning that PKST of U is 0, where U is, we pull back V to torus. And now recall that we had fit and t equal to 0, and then we had an uncoupled system. So fi0 is equal to this. And the gki0 will correspond to the gradient of phi I restricted to this space. And by the corollary, we know that this degree is minus 1 to the power L, at least as long as V is an open bounded neighborhood of the origin. And now also I define V kt. We take the sigma of the ball BR0 intersect UT, and then we intersect it with FK. And VK will consist of V and T, such that V is in VKT, and T is equal to this T. Now, by the a priori bounds, one can see that GKT is an admissible homotopy, and provided R and K are large enough. Admissible means that there is no that there are no zeros on the boundary. So, why is it so? Because on the boundary of BR, there are no solutions because R was chosen sufficiently large. And on the boundary of UT, there are no solutions because this would mean that some kappa I is 0. So by the homotopy invariance, we have that these two degrees are equal. And now GK1 is 0 for some VK here, and for all K large enough. And now we have this equality is equivalent to, or we have this equivalence. So we have PK S1 UK equal to 0 for some UK here and K large enough. And now passing to a subsequence, UK bar goes weakly to U bar, and using compact embeddings, one shows that this is in fact a strong convergence. So we have S1U equal to 0, and this means that U solves our problem. And that's the end of the proof, and that's the end of my talk.
Thank you so much, Professor Andrei Zukin, for this very nice talk. Let's see if you have some remarks or questions from the audience. Not yet, but I would like to ask you, Professor Zukin, in the case, two-dimensional case, n equals to 2, is it possible to deal with exponential growth?
You mean exponential decay?
Yeah. Sorry. Yeah. Exponential decay. Yeah.
Well, as long as kappa I is positive, the decay will be exponential. Yes.
Okay. And what would you say that could be the directions to go further for the development of these results?
Well, it's Well, definitely one direction is to see if these strong restrictions concerning both dimensions and parameters, if they can be weakened. Well, I'm quite sure you can weaken them, but our proof breaks down.
Okay. Yeah, we have here greetings from the audience. So we'd like to thank you so very much again, Professor Zukin, for this your very nice talk. Thank you so much. Bye-bye.
Well, thank you very much. It was my pleasure.
Okay, we will resume in 90 minutes for our next talk. So see you. Bye-bye. Hi there. Welcome to the third lecture in this morning section. It is a pleasure for me to introduce Professor Augusto Ponce from Université Catholique de Louvain, Belgium. He's going to talk about a new type of connected component created by singular potentials. Professor Augusto Ponce has many contributions in nonlinear analysis and partial differential equations, focusing on topics like Sobolev maps into manifolds and nonlinear PDEs and connections with measure theory, among others. His recent book, Elliptic PDEs, Measures and Capacities, is an interesting invitation to the subject and gives an idea of his research topics. Welcome, Professor Augusto Ponce. Thank you for accepting our invitation. It's a pleasure to have you in the workshop.
Well, Gustavo, thank you very much for this nice introduction. It's really a pleasure to participate in this workshop. And it's a pity you can't be in São Carlos right now, but hopefully things will get better soon.
Okay.
Thank you very much.
Our pleasure.
Okay, so let me start my talk. So don't worry about the title of my talk, because I forgot what I gave you as the title. But I'm going to talk exactly what you mentioned. I'm going to talk about a new type of connected components. But what I had in background was the strong maximum principle for Schrödinger operators, and at some point in trying to solve kind of new connected component popped up from our approach, and my talk is going to be focused on this type of component, and the strong maximum principle is going to be in the background actually, because it was actually the original motivation. So let me start with what I call experimental mathematics, where we look some phenomena that things better. So if I take a continuous function
Hello, we are sorry for the trouble with the internet connection of Professor Ponce. We will break now and we will resume at 1:30 p.m. São Carlos local time. And we will try to reschedule the lecture of Professor Ponce. So we break now and hope to see you for our first lecture in the afternoon at 1:30 p.m. São Carlos local time. Okay? See you.